Today we're going to look at density curves. Density curves are a very commonly used device in statistics. Later on we're going to look at some specific ones that are very important, for instance the standard normal distribution or the t-distributions or the chi-square distribution. And we'll have a lot more to say about them at that time. But for now we're just going to introduce the basic concept of a density curve and how it can be used to answer questions. A density curve has these two characteristics. It lies on or above the x-axis, and secondly, the area under the curve is equal to 1, or 100%. Right here we've got a sketch of a generic density curve. The variable that we're interested in here is x, some generic variable, and here is the density curve. You can see it lies on or above the x-axis, and the area under this curve we can assume to be 1. Now, if you're interested in the proportion of x values that fall between two given boundaries, say a and b, we would write that proportion this way in mathematical notation: p parentheses x is greater than a and less than b, and that proportion would be equal to the area under the curve between a and b. We'll do a couple of examples to see how this works. Here is a uniform density curve, and you can see it has a flat top. So here it is. That's it. Lies on or above the x-axis. The area under the curve is 1, as you can see. The area is rectangular. It has a length of 2, a height or a width of 0.5, and 0.5 times 2 is 1. So the area of this rectangle is 1. Now, if you're interested in figuring out the proportion of x values that fall between two boundaries, you can basically use what you know from geometry about the area of rectangles. Okay, for instance, if you want to know the proportion of x's that fall between 0.4 and 1.2, that we write this way: p parentheses x is greater than 0.4 and less than 1.2. You just take the difference between 1.2 and 0.4. That would give you the length of this shaded rectangle right here, and then you multiply it times the height, which is 0.5. So you get 0.8 times 0.5, or 0.4, which is 40%, or 40% of the area under the curve. Okay, but this is actually what the area is. It's 0.4. It's 40% of the whole thing. You can write your proportions either way. If you want to know the proportion of x values that fall between 0 and 0.4, you can just find the area of this little rectangle between 0 and 0.4. It's got a width of, or a length of 0.4 minus 0 and a height of 0.5, and that area works out to be 0.2. I think you can see that since this curve is uniform across the top, okay, basically the area of each of these pieces only depends on how wide the piece is, and you can look at each of these as fractions of 2. 0.4 is 1/5 of 2, and so that area is 20%. This is 0.8, and 0.8 divided by 2 is 40%, and so on. The area to the right of 0.4, that is the area all under the curve to the right of 0.4, is 0.8. And you have 2 minus 0.4 is 1.6, and 1.6 times 0.5 is 0.8. Or you could look at it this way: since this area here to the left of 0.4 is 20%, then the area under the curve to the right of 0.4 has to be 80%. So you can look at it either way. They're both going to work, and feel free to use either method. In fact, when you're calculating proportions under these density curves, use any method that works. You can use anything you know from geometry to help you out, and later on when we get to more specific kinds of density curves like the t-distributions or the standard normal distribution, we're going to benefit from calculations that people have already done to figure out areas under those curves. Here's another density curve. It's triangular. The triangle has a base of 2 and a height of 1. Area is 1/2 of 2 times 1, or 1. And it lies above the x-axis, or on the x-axis at all points. So that's a valid density curve right there. You can see it's right skewed. But it has this shape, triangular. If you want to find the area under this curve, the area between any two values under this curve is basically a trapezoid, and you use what you know about the area of a trapezoid to figure out that area right there. For instance, if you want to know the proportion of x values that fall between 0.4 and 1.2, you can just use the trapezoid area formula. 1/2 the sum of the bases times the height. Now this trapezoid here, the bases are here and here, and then the height is actually distance between 0.4 and 1.2. Now the heights of these, I'll leave it to you to figure out where those come from, but this height right here, or this base on this trapezoid, is 0.8, and this base right here is 0.4, and this distance from here to here is 0.8. So we have 0.8 plus 0.4, which is 1.2, times 0.8, and then we're going to divide by 2, and we get 0.48. So 48% of the area under that curve is between 0.4 and 1.2. If you want to find the proportion of x values that are between 0 and 1, that would be 75% of the area under the curve. In this situation, you could probably use what you know about similar triangles to help you there. You could break this big triangle up into 4 smaller congruent triangles. 3 of them would be to the left of 1, 1 would be to the right of 1. And so at 1, 75% of the area would be to the left, 25% of the area would be to the right. So if the proportion of x values that are between 0 and 1 is 0.75, the proportion of x values that are between 1 and 2, that is under this piece of the curve, would be 0.25. And together they would add to 1.